you worked with the sine function quite a bit. If you remember SOHCAHTOA, our sort of definition of sine was that the sine ratio of some angle is the length of the opposite side divided by the length of the hypotenuse in a right angled triangle. So, I mean, if I were to draw that for you, that has to be 90 degrees. Your angle is down here. That's the opposite side. That's the hypotenuse. So this angle here, it can be very shallow, right? If you have a very long triangle, then this angle is close to 0. If you have a triangle that's very tall, then this angle is getting bigger, getting to 90 degrees. So if you think about that, a triangle can have a corner there that's 89. It can have a corner there that's 89.9 degrees. But if you actually hit 90, right? If that's a 90-degree corner and that's a 90-degree corner, these are parallel and they'll never touch. So this doesn't actually make a triangle anymore. So the idea of putting in any angle here that's bigger than 90 doesn't really make sense for this understanding of what sine is. But if I were to try it in a calculator, we're going to try sine of 120 degrees. Let's pick it up. Make sure that you are in degrees. There should be a little D on your screen there, it says degrees. I'm going to type in sine 120. You do it too. And it spits out this horrendous number. So 0.866. So I'm just going to take note of that. Now, in this understanding of what the sine function is doing, you can't put a 120 degree angle here. That would make the triangle do this, right? That's 120 degrees. So it's not just become parallel like an open container. That side now has tipped past being parallel. So you've taken the triangle and you opened it, and then now you're bending it inside out. But despite that not making much sense geometrically, this is still spitting out a value. So I'm just going to track these on a grid here. I've got sine 120. So if I find 120 degrees, that's here. And my calculator returned 0.866. So I put 1 on this line. So 0.866 is somewhere around here. Not quite 1, but definitely more than 0.5. Okay, well, I'm going to just start generating dots, and I'm going to plot them on this grid, and I'm going to see what I end up getting. So let's start with sine 0. Type that into your calculator. Sine 0 is 0. So when the x is 0, the y is 0 too. That's here. Let's try sine 30. We could do 1, 2, 3, 4, 5 if you like, but considering we already know it goes up to 90 and we need to go past that, that's going to be a lot of dots. So I'm just going to skip by 30s each time. So sine 30 gives you 0.5. So I'm going to find 30 on here. If that's 60, that's 30. And my y value should be 0.5. Puts it right there. Sine 60. gives me a horrendous decimal, right? It's there. I don't know if you can see the screen or not, but it says 0.866, which is interesting because we've already seen that number before. I'm just going to plot it in. 60 on the x, 0.866 on the y. Jump up 30 more, I'd have sine 90. So sine of 90 is 1. So when x is 90, sine is worth 1. We already did sine 120, but I'll write it down here so we have the number in a pattern. Next 30 up would be sine of 150. I'm going to try. Give me 0.5. So 150 would be here. There we go. Next 30 up would be sine of 180. Gives me 0. And I'm down to here. Now, I've generated this nice, completely symmetrical curve. And 180 is a special angle, right? That's 90 degrees. This is 180 degrees. We've gone flat on the other side. So in the transition between this and this, my sine values peaked around 90 and then became 0 again once I was flat. So flat is 0, all the way up to 1, and then all the way back down to 0. Well, what happens if you keep going? So try sine 210, because 180 plus 30 is 210. Put that in the calculator. Gives me negative 0.5. I'll plot that in there. Negative 0.5 is here. And then I will need sine of 240. So that's 30 degrees more. Gives me that same number again, 0.866, but it's negative this time. That's going to be about here. $240, good to go. 30 more, be 270. Sine of 270 gives you negative 1. I keep going, 30 more would be sine of 300. Sine 300 equals negative 0.866 again. Sine of 330 negative 0.5. Perhaps you anticipated that. So apparently I can't count. I jumped by 30 on this last one. So 120, 180, 240, 300, 360. Lines up now. 330 should be right there. And then sine of 360. Type that in. Can you guess what it's going to be? Spits out 0. So I've generated this exact same pattern. It's just under instead of over. Now I skipped a bunch of angles in there because it would have been exhausting to try and calculate them all. But I can represent them by just connecting these dots. Right? There's all the sine values between 0 and 60. there's all the sine values between there and then between there and there. Okay. So I got this pattern that got back to there. I mean, what would happen if you kept going? So the next one, 30 more than this, would be sine of 390. So you try that, sine 390, and you get positive 1/2. Next one up would be 420. Sine of 420 is 0.866. So the pattern is repeating itself. I'm just going to end up getting another set of these. So I'm not going to bother calculating, I'm just going to rough it in there. You've got this thing that goes on forever, waving back and forth. So this shape gets referred to as a sine wave. Because like a wave on the water, it will have a peak, and it will have a trough, and then a peak, and then a trough, etc., going in this direction. If I try the negatives, after here, none of these angles make sense in a triangle because the triangle isn't closed anymore. Angles like this, you've built the base of your triangle, the 90-degree corner, and then this side here, if you've gone 390 degrees, it went all the way around and then back to 30. So it's a triangle that's been spun around. That's confusing. So it's maybe time to stop seeing the sine, cosine, and tangent functions as pieces of triangles, but as their own independent functions that describe any repetitive behavior. So things like a pendulum, right? If you hang something and you let it swing back and forth, back and forth, back and forth, its position relative to the center is positive and then negative, and then positive and then negative. So you would need that. Pendulum swings out, pendulum swings in, pendulum swings out, pendulum swings in. So this function that deals with repetitive behaviors just happened to apply to solving sides of triangles. But it's time for it to sort of grow into its own thing. So I've got the numbers between 0 and 360. Think about that, 360 degrees in a circle, right? That's one full cycle of a circle. It continues after that, always repeating the pattern. What if we go this way? I'm going to try sine of negative 30. I get negative 0.5. Sine of negative 60. I get negative 0.866. Sine of negative 90. I get negative 1. Sine of negative 120. I get, that's 12. Sine of negative 120. I get negative 0.866. And then probably negative 0.5, and then 0, and then 0.5, so that I end up with this wave repeating itself into the negatives as well. So I think the message here, if I were to clean this off for you, the message is that if you were to be given a function like this, so f of x is 4 sine 3x minus 10 plus 2, and you were asked to evaluate f at 250. Well, that's maybe a bit. Let's go f at 80. Put that number in, just like you always do. F at 80 would be 4 sine 3 times 80 minus 10 plus 2. I have to do this first. 80 minus 10 is 70. Three times 70 is 210. And you don't have to panic that this is bigger than 90 degrees. You maybe didn't even notice it when you were doing the algebra skills portion, that you sometimes had to put a number in here that was bigger than a triangle could handle into the triangle function. But now that we acknowledge that it's not a triangle function, it's the sine wave function, this number will be just fine. So when I get to this line, I'm just going to need a calculator to work out that decimal. Sine of 210 gives me negative 0.5. 4 times negative 0.5 is negative 2. And negative 2 plus 2 happens to 0.5. So you've evaluated that this function at 80 degrees is 0. Okay. Evaluating is easy. You just pop the number in, see what you get. We're going to erase this, and we're going to try one where you have to use algebra to solve, which is a touch more complicated. When you allow obtuse angles to be involved, this expression stops being a thing that spits out one answer, and it ends up spitting out multiple answers. So to sort of show you that, I'm going to pull up a graph of sine. So we had this a minute ago. So there's my sine wave. It goes back and forth between -1 and +1 on the y-axis. And this is asking me at what x value does that y value happen. So I'm going to find that y value on my axis. It's right here at 0.5. I'm just going to scan across. Now, you might notice that the curve is that high here, and here, and here. And since this wave goes on forever, it will happen again, and again, and again. Now, fortunately for us, we don't have to write down all the infinite number of solutions. We just need to find these two. If you see this one, there's one there less than 90 degrees, and there's one pinned between 90 degrees and 180 degrees. So the first thing we're going to do is use the arc sine on this, and then consult our calculator and see what it spits out. So beta would be the arc sine of 0.5. So I'm going to type that in here. Arc sine 0.5 is 30 degrees. Now I'm going to look at that graph. I'm going to try and find that there. 30 degrees is right here. So that's this solution. We found this one. The limitation of your calculator is that it only spits out one number. It isn't going to give you the other answer. So you have to think about how you're going to find this one. Now it's just a matter of symmetry. If this thing is symmetrical, then this distance, 30 degrees, must be the same as that distance, 30 degrees. So I just need to know where this hump ends and then back up 30 degrees to get my second solution. So if you look there, the hump ends at 180 degrees. So to get my second solution, go to 180 and back up 30 degrees. Therefore, my second solution would be 180 minus 30 would be 150 degrees. And if you check the scale there, 120, 150, that's where it shows up. Now to finish this off, this solution happens again after a full cycle. So it happens 360 degrees later. Again, it repeats itself. And then it repeats itself another 360 degrees. And then another 360 degrees. So I'm going to put a little variable on here saying this is true at 30 degrees and every 360 degrees after that, taken as many times as you like. Well, this solution, the second solution, also repeats every 360. So I'm going to have to tack that on there too. Okay, now you should always check your work. So just quick, pick up your calculator, try sine of 30. Sine 30 is 0.5. Check sine 150. (0.5). Now, check one of these solutions. 30 plus 1 360 would be 390. Try sine 390. 0.5. So, I've been able to use my arc sine to get one solution and find where it is on the graph. And then use that solution to find a second solution based on the symmetry of this lobe here. And then you have to acknowledge that those solutions repeat every time the lobe repeats every 360 degrees. So we'll try one here where the sign is negative. So first thing I'm going to need then is I'm going to have to look at where my y values are negative. Negative 0.7 is somewhere around here. So if I draw across, there's going to be a solution there, one here, and then they're going to repeat every 360 degrees. I'm going to use my calculator to find one. So beta is arc sine negative 0.743. And it's going to spit out negative 47.9 degrees. Okay, so negative 47.9, that's this one right here, right? Because we had to go to the left on the x-axis. So I need to find this solution or this solution, right? These are the ones on the way down. I already have the one on the way up. So I just need to use some symmetry here. I can go from there to there, which is 47.9 degrees. And to get to this solution, I'd have to go all the way out to negative 180 and move forwards this much. So look at that and think about that. This isn't a formula kind of thing. If you try to use it like a formula, it will get messed up. Look at where you need to go to the other end of that lobe, and then decide if you're moving forwards or backwards. Forwards, you're adding, backwards, you're subtracting. So to get this solution, I would have to go to negative 180 to get to the back side of the lobe. And then I have to move forwards this much because of the symmetry. Forward 47.9 degrees. So negative 180, that's negative 180 plus 47.9 gives me negative 132.1 degrees. And then I just have to acknowledge that these solutions repeat every 360 degrees. I tack that on the back. Okay, I'm going to clear this off. We'll try a cosine that's positive, and I'll let you think about a cosine that's negative, and then we'll do a tan that's negative, and I'll let you think about a tan that's positive. So I changed my mind a little bit. I'm going to do a cosine that's negative, and then we'll do a tan that's positive. So I've made you a graph of cosine here. Looks a lot like sine, but the peaks are in a different place. So the process is the same. I'm looking for where this wave is at this y value. So negative 0.461 is about here. So if I scroll across, I'm going to have a solution there, solution here, etc. So I'm getting these two, repeat these two partnered solutions, right? The descending one and the ascending one. So I'm going to use my arc cos to get one of those solutions. So let's see, shift cosine, negative 0.461 gives me 117.45 degrees. So if I look on my graph here, that's 90, that's 120. So I did get that solution that landed right at 117.45. Okay, here's where it gets a little wild. I've got this length. It's this big. I have to find a symmetrical spot that will allow me to use this length to land on there. So if I try to build where the symmetry is, it's from this peak to this peak. Let's put a box around there. If you look just in there, that pattern is completely symmetrical. And then this distance has to match that distance there because of the symmetry. So how do I get to this place using that distance? Well, I had to go all the way out to the end of the pattern, all the way to 360. And then I had to back up this much. So for my second solution, I had to go to 360 and then back up 117.45 degrees. So 360 subtract 117.45 gives me 242.55 degrees. So I've got those two solutions. And 242, if you look at my grid here, that's 270, that's 240, and that second solution is just a little bit past the 240 line. Just to finish, I have to acknowledge that that pair of solutions is going to happen again and again and again. So I allow that by tacking on any number of 360 degrees I like. Okay, we're going to clear this off and try a tan one, and then we'll be good to go for the practice problems. There's a graph of tan. Don't panic. It does look kind of crazy, but it's just generated by making a table of values like anything else is. I'm still looking for y values at 3.4. Well, let's make that, why don't we make that 2.4? Because then it will fit on my grid. 2.4 is somewhere around there. So if I look across, there's a solution here, 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 here. So I'm going to use my arctan to figure out exactly where that is. And we'll pop that in the calculator and see what it says. .38 degrees. So if you look on my scale, 30, 60, 90, 60 is here, and this is happening just a little bit to the right of that, so that's good. So I have this distance. And if I have that distance, and I have one solution that goes from this weird little shape, right, where it crosses the x-axis over 67.38, then if I go to the next one, right, this is the next place where I cross the x-axis, and look up here. That distance and that distance are the same. So that's how I'm going to get my second solution. So to get to here, I had to travel all the way out to 180 and move forwards another 67.38 degrees. So I had to go to 180 and then move forwards 67.38. Try and keep that off my forehead. Okay, so 180 plus 67.38 gives me 247.38. That's an omega, by the way, in case you're not familiar with all the Greek letters yet. And if I check that on my scale, this would be 240, this is 270, and my solution is happening just a little bit to the right of the 240 line, which is good. I have to acknowledge that this pair of solutions repeats themselves over and over and over again, so plus 360 degrees as many times as I like, and I'm good to go. So I have left the positive cosine and the negative tan for you to puzzle over, but it's the same idea. You just find the y value, dot your way across, see where two solutions are, and then find a measuring point, and then move either forwards or backwards, whatever your calculator tells you for the first solution, in order to land where you need to go.